So the next set of question asks, a DJ wondered if the number of beats per minute in songs from 2015 were lower than beats per minute in songs from 2010. A random sample of songs from each year was selected, and the summary statistics are listed in the following chart. The histogram for the songs for each year appears unimodal and about symmetric. Does the sample indicate that the newer songs have lower beats per minute than songs from 2010? So we want to know what type of test does the DJ need to conduct. So we want to figure out what type of variables do we have. Well, we have year, 2010 or 2015. That's one categorical variable with two categories. And then beats per minute. Which is a quantitative variable. So if we have one categorical variable with two categories and a single quantitative variable, it's either mu1 minus mu2 or mu-d for our parameter. So we just want to figure out, are the songs paired? Can we compare a song from 2015 directly to a song from 2010? It just tells us that there was a random sample of songs from each year, so there's no reason to believe they can be paired together. So if we can't pair them, it's just going to be a two-sample t-test. Then we want to know what are the null and alternative hypotheses. So our hypotheses are going to be about our parameters. The only one that has mu1 and mu2, or mu10 and mu15, is B. 4 says, have the conditions been met? So what we want to check is for our independence condition. So that means we're looking for a random sample or randomized experiment, some sort of randomization. So it says that they took a random sample of songs from each year. So that condition's been met. It says no, the sample is larger than 10% of the population. We have a sample size of 40 and 40. Both of those, if we multiply by 10, are 400. We can probably assume that there are more than 400 songs released in 2010 and 2015. So that condition's been met. And then D says no, the normality condition has not been met. Well, we have a sample size of 40, which is large-ish, but we can see that it says the histogram is unimodal and symmetric. So that condition's been met as well. So then the answer would be A. So we want to know what's the standard error. If we look at our formula sheet, we're doing our parameters mu1 minus mu2, and we see that the standard error is the square root of our sample standard deviation squared divided by the sample size, and we add them together. So anytime you want to know what the standard error is, just look at what's in the denominator of the test statistic. So we end up with the square root of 2 squared divided by 40 plus 3 squared divided by 40, which ends up being about 0.570. 6 says, if the test statistic is 1.75 and the degrees of freedom are 68, we want to find our p-value. So we draw our t-distribution, because we're doing a two-sample t-test. Centered around 0, we have a test statistic of 1.75, and we just want to figure out which direction we want to shade. All of our alternative hypotheses are greater than, so we're going to do a right tail test. So we're going to shade in this direction. So to find the p-value, we need our calculator. I'm going to go to second vars, scroll down to tcdf. Our lower bound is where we start shading at 1.75. Our upper bound is some large positive number. And it tells us the degrees of freedom are 68. If we plug all that in, we get a p-value about 0.042. We don't need to double it because it's not a two-tailed test. If the alternative hypothesis was not equal to, we just want to see if there's a difference between the two, then we'd have to double this to be 0.048. So the answer would be B in that example. But since it's just a right tail test, it's just 0.042. Then we know what is the conclusion type of the hypothesis test with a significance level of 0.01. Well, our p-value is greater than our significance level, so we're going to fail to reject the null hypothesis. So if we fail to reject the null hypothesis, the results are not statistically significant, so that rules out A and B. So C says the result is not statistically significant, and conclude that there is evidence that the average beats per minute per song in 2015 is the same. So C is wrong, because since our p-value is larger than our significance level, we lack evidence for anything. We never have evidence in favor of the null hypothesis, just in favor of the alternative. So the only answer then would be D. The results is not statistically significant, since our p-value is p-value is greater than our significance level. We can conclude that there is insufficient evidence to claim that the average beats per minute in songs in 2010 is different than the average beat per minute per song in 2015. So if we fail to reject, it's always going to have insufficient evidence.